Yes, good morning, class. I'm also wishing you happy new month. This is the month of our test, so let us try and be up and doing. Okay. Last Thursday, I started with IFAS. But we are unable to conclude it because there was outage later. Last week, by way of summary now, we said ethers are derivatives of water, where the two hydrogen atoms of water has been replaced with either an alkyl, two alkyl group, or aryl groups, or a vinylic group. And also we were informed that the most well-known ether is diethyl ether. Diethyl ether is being used medicinally as an anesthetic and is much used industrially also as a solvent. We've done all this last week, and I give examples of ethers. This is anisole. Anisole is methylphenyl ether, where one of the hydrogen of water has been replaced with methyl group and the other one by a benzene or a phenyl group. One of the most important cyclic ether is tetrahydrofuran, known as widely known as THF. Okay. Also, by way of classification, we said ethers can be classified as symmetrical ethers. That is when R is equal to the other R. Okay. Then we have unsymmetrical ether, where R is not equal to the R prime. Okay. Then we have the tetrahydrofuran, which is a cyclic ether. It is a five-membered ring ether. Okay. And also we said that there are rules in naming ethers. The first one, which is the IUPAC rule for ethers. The first rule says the naming of ethers, even though can be complicated by the fact that two different systems are allowed. Okay, but the relatively simple way to name ether is first by identifying the two organic residues or the alkyl groups, then adding the word ether to it. For example, diethyl ether. Diethyl ether, that means the first, there are two ethyl group. That's why it is diethyl ether. There are two ethyl group joining the oxygen on the two sides. Also, we have another example is here, which is the tert-butyl methyl ether, then the ethyl vinyl ether, and then the cyclopropyl phenyl ether, and so on like that. We also we look at the physical properties of ethers, talked about their boiling point, that they have boiling point and melting point that is mostly can be compared with that of alcohol, or the corresponding alkene groups. We also talk about solubility in water, and we said it's not soluble in water. It's not soluble in water, unlike alcohol. Also, we talked about synthesis or preparation of ethers, where we talked about the first one, the acid catalyzed dehydration of alcohols, where when you have 2 mole of, if you dehydrate 2 mole of alcohol, it will give you an ether, especially in the presence of conc H2SO4, and at 140 degrees Celsius, you have an ether. Another very important and the industrial way of preparing ether is by the Williamson ether synthesis. Williamson ether synthesis, where an alkyl halide is reacted with an alkoxide, and then you have an ether. Okay, we also talk about various reactions of ether. Various reactions of ether. Ether can undergo cleavage in the presence of hydrogen halides, especially HCl, HBr, or HI, hydrogen iodide. So in the presence of hydrogen halide, ether is cleaved, and you have 2 alkyl halides. It will give you 2 alkyl halides, and you can see it here, depending on the arbs. And then also that ether can undergo auto-oxidation to peroxide. You know peroxide, that is RO, and by auto-oxidation will give you a peroxide. A peroxide is RO single bond O single bond R. Okay, it can also undergo ring opening reaction for cyclic ethers. And then we also talked about various applications of ether. I will send a comprehensive note as regard ether later. So today we want to look at, we are starting a very new topic, which is the carbonyl compounds. Carbonyl compounds. What are carbonyl compounds? Carbonyl compounds are everywhere in nature, and they are of importance to organic chemistry, organic chemists, or biologists, or biochemists. Why? Because most proteins, carbohydrates, nucleic acid all contain the carbonyl group. And when you are talking of carbonyl group, you are talking about aldehydes and ketone. That is, carbonyl compounds can be divided into 2. We have the aldehyde group or aldehydic group. We have the ketonic, or the ketone. So the carbonyl, though is sp2 hybridized, if you look at it, you have single bond, then double bond O. Okay. The carbon of the carbonyl compound is sp2 hybridized. and of course with a bond angle of 120, as we have for every sp2 hybridized atom. But it's rather different from an alkene. Okay, the C double bond O is different from alkene because the oxygen atom is more electronegative than carbon. Hence, the C double bond O bond in carbonyl is polar. It's relatively polar. In addition, the carbonyl C double bond O is also shorter and stronger than the alkene double bond. This we should note. This we should note. Now, let's pick them one by one. So let's start with, maybe we should just pick, take the two together for a while before we start to dwell on each of them. Now, aldehydes and ketones are carbonyl compounds attached to groups that cannot be replaced by a nucleophile. I'm sure you still remember your nucleophile and electrophile. I taught that in my first class, and Professor Lomola also went further to in teaching you on this. So when the carbonyl is linked to one alkyl group, when the carbonyl, the C double bond O, is joined to just one alkyl group and a hydrogen, then it is called, or the compound is now, the carbonyl compound is now known as an aldehyde. But when the carbonyl or the carbonyl is connected to two alkyl groups or a ring residue, then it is a ketone. It will be a ketone. Now, both aldehydes and ketones have the general formula CnH2nO. CnH2nO. That's the general formula. So if N is 1, then your simplest aldehyde or carbonyl compound will be HCHO. That is methanal. Methanal. That's the simplest aldehyde. That is when the N is 1. Okay. When N is 1, then you can't have any other compound than an aldehyde. But if N is 2, then you can have either an aldehyde or a ketone. Okay, you can have either an aldehyde or carbon N is equal to 2 will also give you, ethanal. CH3 C double bond O. Okay, that is ethanal. That means for N is equal to 1 and 2, you can't have a ketone, but an aldehyde. But as from when N is equal to 3, then you can have both the isomer aldehyde and ketone. For example, you can have propanol or acetone, that is propanone. When N is equal to 3, then you can have propanol or propanone. Now let's go further. Now aldehydes are represented generally as RCHO. That is, it contains one alkyl group, also one hydrogen, and then the C double bond O, which is the carbonyl functional group. Okay, and also that as RCHO, then the functional group is terminal, while the non-terminal will be ketone, which is RCOOR prime. RCOOR prime. R prime, and this is a ketone. R prime joined to C double bond O. So the polarization of the carbonyl group contributes to the properties and reactivities of ketone. As you can see in the diagram here, an electrophile, we attack the carbon of the carbonyl, and then the oxygen will go to pick a nucleophile. Okay, that means the hydrogens of the alkyl groups can be termed acidic proton. Can be termed acidic product. So other carbonyl compound or carbonyl containing compounds that we have are carboxylic acid, esters, acid anhydrides, acyl hydrides, and amides, but they are not called carbonyl compounds. Okay, they just have a carbonyl functional group, but they are not carbonyl compound. Carbonyl compound are strictly aldehydes and ketone. Aldehydes and ketone. Others, like I said, carboxylic acid, esters, acid anhydride, acyl halides, and amides only contain a carbonyl functional group, but they are not carbonyl compound. Can we move further? Okay, maybe I should just drop my first attendance code now. My first attendance code is EHX K5, all in uppercase, all uppercase, all uppercase. So that is my first attendance code for you. Now, let's look at naming of carbonyl compounds, and we'll start with that of aldehyde first. Of course, like any other chemical compounds, we have the trivial names as well as the IUPAC names. But let's start with the trivial names, which are usually derived from the corresponding carboxylic acid. For example, this first one is formic acid. Okay, formic acid. So the corresponding aldehyde is formaldehyde. 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 Now look at this one also. We have 3 carbon. We have the acid is propionic acid or propanoic acid. Now the corresponding aldehyde will be propionaldehyde. Propionaldehyde. Also, we have this one, and so on and so forth, like that. This is the acid, and this is the corresponding aldehyde. Now, let's look at the cyclic one here. This is benzoic acid. Benzoic acid, and the corresponding aldehyde of benzoic acid is benzaldehyde. So all these are trivial names. Now, let's look at the IUPAC. I told us there are 2 naming systems, the trivial one and the IUPAC one. Now, the IUPAC nomenclature, here you need to drop the final E and add R. You drop the final E of your alkane and you now put R. For example, this is propane. Propane is CH3, CH2, CH3. And then the corresponding aldehyde of propane will be propanal. So the third carbon now is bearing the C double bond OH. So it is now propanal or propan-1-al. Propanal or propan-1-al. Let's look at the second one also. The corresponding alkane here, or the parent alkane here, we have 1, 2, 3, 4, 5 carbon. Of course, there are 6 carbon, but the 6th carbon is a substituent on carbon 2. So the name of this alkane is 2-methylpentane. 2-methylpentane. And the corresponding aldehyde will be 2-methylpentanal. 2-methylpentanal or 2-methylpentan-1-al. But when the functional group is on carbon 1, we don't normally, but if you put it, there is no offense. Okay, so it can be 2-methylpentanal or 2-methylpentan-1-al. Now, what are the rules guiding this naming? The longest chain carrying the carbonyl group is considered the parent structure. Then carbonyl compound is made carbon 1, just like we have here. You can see 1, this is 2, this is 3, this is 4, and this is 5. Okay, and that is why it is 2-methylpentanal or 2-methylpentan-1-al. Okay, let's move further. For the ketone, now we are on the ketone, and also for ketone, the same principle follow. That is, we have the trivial name, and also we have the IUPAC name. So let's start with the trivial name. Trivial naming can be used such that both alkyl groups are named followed by ketone, just the way we did for aldehyde. Okay, now look at an example here. This first one, we have 1, 2. Okay, by trivia, we don't even need to number the carbon. We just look at the alkyl groups. Okay, so we have methyl, then ethyl here. Methyl here, ethyl. So the name is methyl ethyl ketone. Methyl ethyl ketone. And also look at this one. This one, the two alkyl groups are same. That is, it has the same methyl group as the two alkyl groups. So we call it acetone. We call this one acetone. We call it acetone, or maybe if you like, you can say dimethyl ketone. Dimethyl ketone. But the acetone is much more accepted. Okay, then let's look at this one. Look at this one. We have we have an isopropyl, 2 isopropyl substituents on the carbonyl. So this one is diisopropyl ketone. Trivial name is diisopropyl ketone. Now, normally substituents are designated by Greek letters, and therefore for this one here, we have methyl beta chloroethyl ketone. Methyl beta chloroethyl ketone. Why is it beta? This first carbon joining the functional group is called the alpha carbon. It's known as the alpha carbon. And the second carbon away from the carbonyl functional group is called beta carbon. So therefore, the chlorine is attached to the beta carbon, and that's why it is called trivially as methyl beta chloroethyl ketone. Okay, now let's look at the aromatic ketones here. We have two of them. The first one, that is, they are called aryl ketones, and they are named as substituted phenones. Okay, this group is called aceto. So the name for this first one is acetophenone. Acetophenone. Okay, and then we have two aryl groups attached to the carbonyl functional group. And for this one, we call it benzophenone. 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 Okay, now let's look at the IUPAC naming system. The IUPAC naming system. Now, how do you name your carbonyl compound or ketone using the IUPAC naming system? Now, what to be considered are the longest chain carrying the carbonyl group is considered the parent structure. So the final E of the parent alkane is thereby dropped and on is added. And position are also must be designated with numbers. Okay. Okay. Now let's look at the examples here. The first one. Okay, so to name this using the IUPAC system, we must number the carbon atoms, and give the smallest number to the carbon bearing the double bond O. That is, the carbonyl functional group should be given the smallest number. So if we start naming from the right, it will be wrong because it will be 1, 2, 3. Then the carbonyl will be carrying number 3. But if we start naming from the left, then we have 1, 2, 3, and 4. Okay, that is the correct way because we are given the smallest number. We are given the smallest number to the carbonyl functional group, and therefore the name is butanone or butan 2-one or butan 2-one. You can call it butanone or you say butan 2-one. Any of the two is correct. Now, let's look at this very long one. Okay, just like I said, give the smallest number to the carbon bearing the oxygen, that is the carbonyl. So we start numbering from right this time around. So this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Here we need to pause. Carbon 5, 6, 7, or 6, 7. So any longest chain, you follow any. So we can follow any here. If you follow up, 6, 7 is correct. If we follow the left wing, 6, 7 is correct. So the name for this one is, that means the substituent on carbon 5, which is the ethyl group, is a substituent on carbon 5. So the name now is 5-ethyl 3-heptanone. 5-ethyl 3-heptanone or 5-ethyl heptan 3-one. 5-ethyl heptan 3-one. So any of the two is correct. Also looking at the the ketone with the cyclic functional group, you have this a cyclohexane carrying a carbonyl, a C double bond O, and also a methyl group. Now, like I told you, the carbon bearing the C double bond O must carry the lowest number. So you give that carbon number 1, then 2, then 3, then 4, then 5, then 6. You can see we go anti-clockwise here. You cannot go clockwise. If you go clockwise, that means you are going to give methyl. Methyl will become carbon number 5. And you must try and give both the carbonyl and the substituent the lowest number possible. So for this one, it is 3-methyl cyclohexanone, 3-methyl cyclohexanone, or 3-methyl cyclohexane. All right. Let me see your comments. If don't have any problem, okay, fine. Okay. Okay, everything is fine. Okay. Yes, everything is fine. I don't know. Say make he go back. Yusuf, what do you mean by that? You say why anti-clockwise? I said we can go either clockwise or anti-clockwise. It doesn't matter. What matters is you must go either clockwise or anti-clockwise to give the carbonyl functional group the smallest number, as well as the substituent. So you can see for this methylcyclohexane, if we go clockwise, then giving 1 to the carbonyl, then this will be 2, this will be 3, this will be 4, then the methyl will be 5-methyl. So 5-methyl, I think 5-methyl cyclohexanone will not be correct. So if I give you this in the exam, if you pick 5-methyl cyclohexanone, it is wrong. You get it wrong. So you must give the substituents and the carbonyl functional group this lowest possible number. The lowest possible number. And for this one, the best way is to go anti-clockwise. All right. Can we take our second attendance code? Our second attendance code is RP, W, B, and M. Okay, RP, W, B, M. Okay, I posted it. RP, W, B, M. It is there for you. So please, now let's move on. Let's move on. I don't. It's not going for. Okay. Let's go further here. Now let's look at preparation of carbonyl compounds, but we start with that of aldehyde. Preparation of aldehydes. Preparation of aldehyde. Aldehyde can be prepared by oxidation of primary alcohols, which we give an aldehyde. Okay, if we oxidize a primary alcohol, then we obtain an aldehyde, while oxidation of secondary alcohols will give ketones. So we must know this. Let's keep this at heart. Now look at this is a primary alcohol. The OH is attached to carbon that has other two hydrogen attached to it. So that makes it a primary alcohol. So if you oxidize it in the presence of oxygen using a very good oxidizing agent, such as Jones reagent, which is in the presence of K2Cr2O7 in H2SO4, then your primary alcohol will be oxidized to aldehyde. It said this Jones reagent can be used for oxidation of primary alcohols with 4 carbon atoms or less, while Collins reagent, which is chromic plus 2-pyridine in dichloromethane, or what we call PCC. PCC is pyridinium chlorochromate in DCM. DCM is dichloromethane. This can be used with for alcohols with longer carbon atoms, but for alcohols that have 4 carbon atoms or less, you can use Jones reagent, while PCC can be used for which is known as Collins reagent, can be used for alcohol that has longer carbon atoms. Okay, and they are, and PCC is a mild oxidizing agent. Now look at this one. This is a secondary alcohol because the OH is attached to a carbon that carries only 1 hydrogen aside from the alkyl group. So if you oxidize this, it will give you a ketone. So this is a ketone, to give you a ketone. But for secondary alcohols, okay, let's see. Okay, another way of forming an aldehyde or ketone is by ozonolysis. You know, we said the first one is by oxidation of primary or secondary alcohols, and that will give you aldehyde and ketone. But another method of preparing aldehyde or aldehydes and ketone is by ozonolysis. Now, depending on the original, ozonolysis of an alkene. Now, depending on the original alkene substitution pattern, ozonolysis followed by reduction cleaves an alkene double bond to give ketone and aldehydes. Now, let's start with this simple one here as an example. This is 2-methyl-but-2-ene. This is 2-methyl-but-2-ene. 2-methyl, that is carbon 1, carbon 2, carbon 3, carbon 4. And therefore, this one is a substituent on carbon 2. So I said the name is 2-methyl-but-2-ene. Now, in the presence of ozone, O3, in dichloromethane, CH2, Cl2, or DCM, this is also known as DCM. Okay, you get this, the double bond is cleaved, and 1 oxygen is attached to each of them. Okay, and you can see this is the same, this is aldehyde, and this side is ketone. So from 2-methyl-but-2-ene, an aldehyde, which is ethanol, and also a propanone or acetone is obtained as the product of ozonolysis of 2-methyl-but1-ene. Now, let's look at the mechanism. The mechanism is here. Okay, the C double bond O, the carbon. Let me show it here if I could. C CC, and then oxygen, 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 and oxygen. So we have it this way, and which is this, and this is called the intermediate. It's called ozonide. This is called ozonide. Ozonide, or if you now, I mean, okay, this is the ozonide. The intermediate is actually the alkene, the C double bond O surrounded by 3 oxygen atom up. But there is, in the ozonide, there is a rearrangement. There is a rearrangement here where you have a C O, single bond O, single bond C, then single bond O, then single bond C. This is called the ozonide. This is called the ozonide. Therefore, at the end of the day, the ozonide subjected to hydrolysis in the presence of zinc in acetic acid will lead to the product that we have up here. The product up here will be the resulting product of the ozonolysis of complete ozonolysis of 2-methyl-but2-ene. 2-methyl-but2-ene. So I'm giving you another one, which is here. Okay, when you have a cyclic alkene, this is 1-methyl-cyclohexane. This is 1-methyl-cyclohexane. In the presence, when you subject it to ozonolysis, the complete product, we have one product here. Unlike up here that we have two products here, one aldehyde, one ketone. One of the things you should take home or you should remember is that when you subject a cyclic alkene to ozonolysis, one product you will get. Okay, the product will be just one. Okay, you can see that 1-methyl-cyclohexane, when you subject it to ozonolysis, you have one product, which is 6-oxoheptanal. That means there is a kind of ring opening. There is a kind of ring opening. Okay. Number 3 way of preparing aldehyde or ketone is by hydration. By hydration of alkynes. Alkynes are triple bonded hydrocarbon, okay, unsaturated and hydrocarbon. And I'm sure Professor Olomola taught that. Now, hydration of alkynes, hydroboration, oxidation, and oxidation of an alkyne gives an anti-Markovnikov addition of water across the triple bond. Okay, if you recall very well, Professor Olomola taught this in his class. So go and revise and then come and then read this. Then you understand very well what we are saying very well here. Now, diborane, also called this imiborane, is used as, it's used for hydration of alkynes. Okay, this bulky borane cannot add twice across the triple bond. Therefore, on oxidation of the borane, the unstable enol are quickly tautomerize to give aldehyde. Now, look at this. This is butane. Butane is a terminal alkyne. This is carbon 1, carbon 2, carbon 3, carbon 4. So in the presence of this amyl borane, and in the presence of peroxide and sodium hydroxide, this intermediate is obtained. This intermediate, which is an enol. What is an enol? Enol is a compound that contains both double bond and then alcoholic or OH functional group. That is why it is called enol. In double bond, then all OH. So the butane is converted first in the presence of this amyl, borane, and peroxide and sodium hydroxide to an enol. If you like, you can call it butanol, butanol, okay? And subsequently, because enol is very unstable, therefore it will tautomerize to give an aldehyde, to give this aldehyde, which is what? Propanol. So the hydration of butane will give you butanol, will give you butanol. Okay. Also, if you want to have the ketone analog of what we of alkyne, then sulfuric acid and mercuric ion will catalyze the hydration of a terminal alkyne, which gives a Markovnikov addition of water across the triple bond. You can see the first one is an anti-Markovnikov addition of water across the triple bond. But using sulfuric acid and mercuric ion as catalysts, the hydration of a terminal alkyne, this one gives a Markovnikov addition. So you should note this. If I were you, I will underline this in my notes. And this leads to the formation of an unstable enol, just like we had the other time. This also is butane. In the presence of this, instead of an aldehyde, we have a ketone. A ketone is obtained. So you can check and see the difference. In the presence of this amyl, borane, peroxide, and sodium hydroxide, you have an anti-Markovnikov addition across the triple bond, and then your resulting carbonyl compound will be an aldehyde. While if you use sulfuric acid with mercury sulfate or mercuric ion as a catalyst in the presence of water, a Markovnikov addition of water across the double bond will be obtained, and this results in a carbonyl compound known as ketone. I hope let's take note of all this. Now, another method, or method number 4 of preparing is by Friedel-Crafts acylation. Yes, let me take a pause here and look at our comments. Do you have any comments for me? Okay, do you have any comments, any question? Okay, before I move on. All right, so let's look at the fourth method of preparing a carbonyl compound, whether aldehyde or ketone. The fourth one I said is Friedel-Crafts acylation. Friedel-Crafts acylation is a good way of synthesizing a diaryl ketones or alkylaryl ketone. Aryl means you have phenyl group, and when you have alkylaryl, that means one alkyl group and one phenyl group. Okay, this is an alkyl group, and this is a phenyl group here. So this is in the presence of acyl chloride. This is an acyl chloride. Reacting it with a an aryl group, which can be benzene. That is, if G here is hydrogen, then you have benzene. But if the G is a halogen, then you have halobenzene or benzene halide, or any activating group. Okay, so Friedel-Crafts always, for this takes place in the presence of aluminum chloride as the catalyst. So this reaction will give this aryl or this alkyl aryl group. Okay, and that is a ketone. That is a ketone, or this other one. So this one, we have our product to be a ketone. Okay, and also we can have, if you react para-nitrobenzoyl chloride, that is position 4, para-nitrobenzoyl chloride with a benzene in the presence of aluminum chloride. Then a para-nitrobenzophenone, that is, we have both the two alkyl group to be phenyl group, nitrophenyl and phenyl group, and therefore the product is also a ketone, but this time a para-nitro ketone, benzophenone ketone. Now, another which is a variant of the Friedel-Crafts acylation, is called Gattermann-Koch synthesis. Gattermann-Koch synthesis is a variant of the Friedel-Crafts acylation in which carbon monoxide and HCl generate an intermediate that reacts like formyl chloride. It reacts like formyl chloride. Okay, now this is a benzene. In the presence of carbon 2 oxide or carbon monoxide and HCl, in the presence of this catalyst here, aluminum chloride and copper chloride, copper 1 chloride. See, the product is a benzaldehyde. This is benzaldehyde. Benzaldehyde. So here we have either a benzene or an activated benzene is also always required. Okay. Now, what happens here is the carbon monoxide and the HCl react together. The C triple bond O, which is carbon monoxide, and HCl react together to give this formyl chloride. It gives formyl chloride, and the formyl chloride will now react with the benzene to give the benzaldehyde. It is known as Gattermann-Koch synthesis, which is a variant of Friedel-Crafts acylation. Okay. Now, let's quickly look at, before I round up, let's look at physical properties. Tomorrow we look at chemical properties or reactions of carbonyl compound, but today let's quickly go through the physical properties. Can I just let me give my third let me give my third attendance code. My third attendance codes now, which is TJU GP. TJU P, all upper case, all upper case. It's there now. So I have like 6 minutes to, let's quickly run through these physical properties of aldehydes and ketone. Aldehydes or ketone, they possess the ability, neither aldehyde nor ketone possess the ability to hydrogen bond with other molecules like themselves. So consequently, it means that boiling points for aldehydes and ketones are lower than that of alcohols of similar molecular mass because they cannot hydrogen bond, just like alcohol would do. So therefore, you know that hydrogen bonding leads to high boiling point. Okay, then the C double bond O in these molecules, they are polar, and so dipole forces exist, and as a result, their boiling points tend to be higher than that of alkanes of similar molar mass. Okay, then water molecules can also interact in a way with the oxygen of the carbonyl, even though it will not interact with the non-bonding pairs of the carbonyl group. So in general, the greater the carbon chain length, then the lower the water solubility, or what we call, or much better, let's put it at the compound becomes less polar. It becomes less polar. Become less polar. Yes, I think this is a very convenient place to stop. I will drop notes on ether, on alcohol, ether, and on carbonyl compounds for you. And we start tomorrow from chemical properties of aldehydes and ketones. So good morning, class. I'd like to see.
Good morning, class. We want to start physics 102 now, general physics 2. How many of you are with me? Yes, thank you very much. Agbala John. Okay, my name still remains the same, Ezekiel Omotoso. And if you can still remember, I taught you physics 101 as well. And I'm actually the coordinator of physics 102 as well. And I want to actually congratulate some of you, or can I say more than 90% of you actually pass physics 101. And I want to believe that you actually make me proud by actually doing excellently well in physics 102 as well. So you know what I always tell you to call me. Yes, you can see there that Ezekiel Omotoso is my name, but I prefer Ezekiel. So, and at the same time, with this physics 102, I'm going to actually discuss 3 topics with you. I'm going to start with magnetic field. When I'm done with magnetic field, I'm also going to discuss magnetic fields due to current. Also, I will discuss induction and inductance with you. But I am very sure majority of you will be thinking, why do we need to actually study magnetic field? You may be thinking that magnetic field is only for science students only. Oh, it's only for science students, it's not for medical students, it's not for biological students, it's not for agricultural students. But may I actually tell you that if you are actually agricultural student, uh, biological student, maybe you are in medicine, you are in pharmacy, I need to tell you that you need magnetic field. For example, I don't want to bore you because I believe those in physics, those in chemistry, those in sciences know that they need magnetic field. But those of you in maybe in sciences, you may be thinking that you don't need magnetic field. But may I tell you that you need magnetic field because there's application of magnetic field in magnetic resonance imaging. Also, there's application of magnetic field in magnetic drug targeting for those that in pharmacy. And then also, you can actually know nowadays that cancer is actually very prominent. Magnetic field can actually be used to actually treat cancer, that is in form of a magnetic nanoparticle that can actually generate it when exposed to alternating magnetic field. Am I communicating? So I want to tell you that either you are in biological sciences, you are in agric, you need this magnetic field. Not only that, also, let's assume that you are in the agricultural faculty. You thought you don't need magnetic field. May I tell you that you actually need magnetic field to actually enhance the germination of your seed. And not only that, you actually need magnetic field in terms of water treatment. Also, you need it in terms of soil analysis. Peradventure, maybe you are also in maybe environmental faculty. You may be thinking that maybe you don't even need magnetic field. May I tell you that you actually need magnetic field in form of groundwater and geological investigation. You need it in environmental pollution monitoring. You need it in waste management, and so on and so forth. So if I should just ask you, how many of you have actually seen magnet before? And I'm very sure you can, all of you will tell me, oh, we have seen it before, we have seen it before. Or peradventure, you have not seen it before. I'm very sure you have seen it, you have seen one before. So if you get home, look at the door of your, or maybe of your parents' fridge, you will see something that they actually place on top, place by the side of that door. You will see that it's actually magnet. So that is why is what I always tell my students, that when we are talking of magnet, when you're talking of physics, physics is something that you have actually come across before. There is no new thing. It's what you are doing every day. So now, in order not to waste your time, let me now go into the lecture. So the first thing I want you to know, what I want you to know is this, that okay, so now, since I've told you that we are going to start with magnetic field. So under the magnetic field, there is something that I have to discuss with you. I believe majority of you know physics. So what is physics behind magnetic field? And what actually produce a magnetic field? And not only that, I will also explain the definition of magnetic field. I will also explain what you know as a discovery of the electron in form of the cross field in form of discovery of electron. It's just like we want to actually discuss, under that we want to discuss, is it possible for electron inside a vacuum to deflect magnetic field? That is what you are going to discuss under cross field, first one. And the other cross field, we want to see how many of you have seen wire electric cable at home before. You have seen it, I believe. So we want to actually see, under the Hall effect, can that electric wire carry current? Can it deflect magnetic field? Okay, so I will discuss something on cyclotron. I will discuss something on the synchrotron. I will also discuss magnetic force on a carry current wire, third, and as same thing as a magnetic dipole moment. Okay, am I communicating? Yes. Okay, thank you. So now, just to start with, what is physics? I believe all of you understand physics. And I want to know, I believe that my colleagues that actually taught you electric field, he has discussed something, he discussed something with you, that physics is just the study of how an electric field can produce an electric force on a charged object. That was what he taught you. So, but if you now look at it in a closer way, can we relate? Because there is field at the back of electric field, and there's also field at the back of magnetic field. Can we actually relate the two together? So we can now say that physics that of a magnetic field is how magnetic field produce magnetic force on a charged particle. But may I tell you, under the electric field, it can actually produce force even if the charge is stationary. But in the case of magnetic field, I need to tell you this, that it can only produce magnetic force if there is motion. If it is not static, if it is static, it won't produce magnetic force. Okay, also it can actually produce magnetic force on a magnetic object such as magnet. And I've actually asked you before, and you said you have come across, you have seen magnet before. Oh, thank you very much. You remember, I'm actually happy for seeing Adeniran comment, Ezekiel, calm down. Good. I'm happy to add that you remind me that. So I've told you, when I'm a bit fast, just tell me that Ezekiel, calm down. Yes, I have almost like a 6 to 7 contact hour with you. I'm going to calm down and explain and make sure you understand it. Because I've told you that you must make me proud. I want to have, if possible, 99% pass this time around. Thank you. Okay, so the science of magnetic field is actually physics. And the application of magnetic field is engineering. If you can still remember, I've actually started with this one to tell you the application of magnetic field. So for we in science, the application is science. So, but for those in engineering, their own is application of magnetic field. And I've actually told you people from sciences and Greek, I've let you understand the importance of magnetic field. I am not just here to waste your time. I'm here to tell you how you are going to apply this magnetic field to your area of specialization, to your field. Thank you. So both the science and the application begin with the question, what actually produces a magnetic field? And I know you have been taught that, under the electric field that we believe that is electric field that actually produce magnetic field. But in case of magnetic field, there is a little modification to that. Okay, so now let's now go a bit to another slide. Magnetism. Before I just want to keep you in suspense first. I won't tell you what actually produce magnetic field. I want to actually let you understand the magnet itself. So you remember that when you are taught electric field, you know, we have two charges. We have positive and negative charges. And you remember vividly, maybe from the high school or from where what you have actually read, that we believe that like charges, like repel and opposite attract. That is when you have positive and positive charges, they are going to actually repel each other. But when you have positive and negative charges, they are going to actually attract each other. The same thing applicable to magnetic field. So when you're talking of magnet, there is no way you can see a magnet with only one pole. That is also going to be dipole in form of north and south. So instead of you putting plus and negative, let's just say, oh, we have north and we have south. So we can now say that south and north. So when we bring when I was still very young, I don't know, maybe you have done the same thing before. I remember that we brought two magnets together. When you are trying to bring two magnets together, you will see them that they will be repelling. Oh, I don't want to join together. I don't want to join together. They will be pushing you. You will be seeing a force pushing you apart. That's so that you are trying to actually bring north and north together. And they said, no, I don't want to join together. I want to be away. So, and the same thing when you are putting north and south, you may not even know north. You may so maybe for you to know north pole or south pole, when you bring two magnets together again, and they say, oh, before you actually join them together, they say, oh, I want to join together. I want to join together. That's so that you are actually bringing two opposite poles together. Am I communicating? Thank you very much. So what I'm trying to say here is that for magnet, you cannot have one pole. You can only have two poles with north and south. So that is north and south, different pole actually attract. So whereas when you have two different poles, they always repel each other. Is that okay? Thank you very much. Okay. So if we now go a bit further, how are you going to know the direction of the magnet itself? How are you going to know if this one is south, if this one is north? So now, if you bring a magnetic field, it's going to actually, it's just like when you have a magnet and you have a compass. That compass contains maybe a tiny needle. A tiny needle. Oh, don't call me Dr. Ezekiel. I've told you, call me Ezekiel. So, Omobori Owo, call me Ezekiel, not Dr. Ezekiel. Thank you. So, what I said earlier is this. I said when you have a compass with a very tiny needle and you place it, so the direction at which that compass is actually going, that's so if it is actually north or south. If it's actually going out, you see the flexion actually going towards the other side. That's so that is not pole. That is, a magnetic field exists in the region around a magnet. So let me just try to recall. Let you to remember what you have actually done before. You have a magnetic bar and you have a magnetic material, let's say your knife or your iron fork or your iron spoon. When you are trying to bring it, maybe it's far away before and you have a magnetic bar. When you bring it closer, when you are a bit closer to that magnet, you will see one force trying to draw you closer. That means you have reached the region of magnetic field. Am I communicating? So that's why when you reach that region where the knife is saying, oh, I want to go closer, I want to go closer, I want to go closer, that you are actually at the region where magnetic field exists. Am I communicating? So now, with what you know in high school, all of us will still remember that when we are talking of magnetic field, is a vector. Why do we call it vector? I believe my students still remember that vector has both magnitude and direction. So, so the direction of magnetic field at any point is in space is the direction indicated by the north pole of a small compass needle placed at that point. So first now, I want to be sure if my students are with me. I want to give you the code, the first code now. Are you ready? The first code now is, are you ready? Can I dictate it? Okay. 5 H Y P. I want to type it now. 5 H Y P. I want to believe you got the code. Yes. Freedom Oluwafeyi. Thank you very much. You got the code, right? 5H YYP. Okay, let's now continue from where we actually pause. So now, if we now go a bit ahead now, I've told you about magnetic field. It's just like when you have a knife and you have a magnetic magnet, and you bring iron or magnetic material closer. No, you did not get Joshua is not one. I said 5H YYP. Okay, thank you. Not B. P for Paul. Okay, P for Paul, not B for ball. Okay, thank you. So let's now continue. So under the magnetic field, we want to believe that the earth is associated with a magnetic field, because you have heard before, they say, oh, one particular country is at the North Pole, the other country is at the South Pole. So that's so that the pole of magnet attract to the earth north geographical pole. That is the magnetic pole, magnetic North Pole. And the same thing with the magnetic South Pole. So I want to know, before I was trying to tell you that what actually produces electric field, we believe is electric. What produces the electric field? What produces electric force? We said electric field produces. So now, in the case of magnetic field, there are two ways to produce magnetic field. The first one is, this is not 104, it is 102. Thank you. So there are two ways to produce magnetic field. The first one is when using moving charge particle, such as a current. How many of you have seen the loudspeaker before? So I remember when I was still young, we always look for a way to actually dismantle the speaker inside we actually dismantle our old radio then, and we bring out the speaker out. And if you look at that particular speaker, when you look at the speaker, you will see the magnet at the back of that speaker. So now, if you now connect wire to that particular speaker, so that if you use moving charge particles such as current, you pass current in a wire to make an electromagnetic. So I will still explain this one better before maybe in the next class. So also, we can also produce magnetic field when we use elementary particles such as electron, because they have intrinsic magnetic field around them. So as we use the electric field to explain and visualize electric force in space, the magnetic will be used to actually explain and visualize magnetic force. We want to actually know how can we determine the magnetic force in space. So in conclusion of this particular aspect, we can say magnetic field lines point in the same direction that North Pole of a compass would point. Okay, so now if we now go a bit further, as I've said earlier, when I was trying to explain to you, under the magnetic line, field line, I said you have a magnetic bar. You have something that we call, how many of you know iron filing? It's just like, oh, you have not, oh, you have never been to farm before. Oh, as though you have been to farm before, there's something like when you sharp your knife or iron or your cutlass, you see some particle, iron particle, just tiny iron particle. That's what we call iron filing. So if you have that iron filing and you bring it and you sprinkle it on a magnet bar, so you will see all those tiny attached to the north side and attached to the south side. And if you see if you look at their arrangement, you will see something like, but if you look at it maybe critically, you will see the way they are actually arranged. So that arrangement, so that you are going to see something like a line, join. That is going out from north, go inside again into the south. That is what we call magnetic field line. But may I tell you something? Under the bar magnet, all those that magnetic field line, they can never cross one another. So that is, the magnetic field at any point is what is going to be tangential to the magnetic field line at that point. And may I tell you also, I say the line originating from the North Pole and end on the South Pole, they do not start or stop in the middle way. They cannot start, they can only start from the north side and end at the south side. That's so that they will not stop the middle way. They cannot actually start from the middle way, and they cannot cross each other. So we can now say the strength of that particular magnetic field is proportional to the number of lines per unit area that passes through a surface oriented. But in the case of this one, is going to act perpendicular to the line. So we can now say the magnetic field line will never come to cross each other. Am I communicating? I hope I'm not too fast. Yes or no? I believe you will say yes. So, and I believe, I will see some of my friends will say no. And you know, I always tell you that when you say yes, that means my student actually means no. But I hope you are not saying no this time around. Thank you very much. No, yeah, your no is yes, I believe. Your no is yes. Okay, thank you very much. Okay, so let's go a bit further. I hope I'm not too fast. Let's go a bit further because time is not on my side as well. So we have said something earlier. We said what produces a magnetic field. We can say we made mention of moving electric charge particle, such as current, produce a magnetic field. We also mentioned electron have intrinsic magnetic field, also produce a magnet. So now, because an electric field is produced by electric charge, we might be thinking or be expecting maybe a magnetic field is also produced by magnetic charge. No, in the case of magnetic field, it's not being produced by magnetic charge. Although individual magnetic charges called magnetic monopole are predicted by certain theory, their existence has not been confirmed. Okay, so that's why let's just stick to what has been confirmed. That is moving electric charge particle, such as current, produce a magnetic field in form of electromagnet. And the same thing also applicable to electron have an intrinsic magnetic field around them, produce magnetic field as well. So you still remember that the way I used to ask you question, everything in physics is not calculation. You know, there is a way of confusing my students now. But I believe if you are in my class today, there is no way you will be confused with this, because I can say maybe magnetic charge can also produce magnetic field and put it in one of your options. But and I always when I put it there, but I believe what I've told you today, you know that what that what has been established that can produce magnetic field is moving electrical charge particle in form of current can produce magnetic field, and the other one, electron that is a elementary particle such as electron can also produce magnetic field. Do you understand it now? Thank you. Okay, let's now try to explain the definition of magnetic field. You know, one thing I like about physics is that physics is not abstract. Physics always want you to understand some things, and we like to quantify things in physics. So, in order to start how to actually quantify that magnetic field, we are going to actually discuss the definition of magnetic field. And when you see the symbol of magnetic field, if I write B and I put arrow on top of it, mind you, you know I'm actually referring to that it is not a scalar, it is a vector. That is, it has both direction and magnitude, yes or no. So, and if I actually write that B and I bold it, so make sure you understand that I'm actually referring to a vector. So we can recall that magnetic field line, as I've told you before, it will point away from north and toward from south pole, as you can see it here. So, and also mind you, I said that magnetic field can never start midway and can never stop midway. Okay, so and they cannot cross each other. I hope you are following. Thank you. So the unit of magnetic field, as we all know, is Tesla. And what is that Tesla? So to remember the Tesla is just a unit of field. That is, the unit of field are force per something. What is that something? So we can also say the Earth magnetic field has a magnitude of approximately 0.5 Gauss. So, and in olden days, they can actually, maybe not in the olden days in America, they are still using Gauss as a unit of magnetic field. So maybe in first way, maybe if I want to actually see if my student is actually following, I can actually give you some simple problem and actually put the unit in form of Gauss. And mind you, and I'm actually expecting you to actually convert that Gauss to Tesla. And 1 Tesla is equal to 10 raised to power 4. Am I communicating? How many of you are still following me? I want to see your response. Are you still there? If you are there, type yes, yes, yes. I want to know if you are there. Oh, thank you, thank you, thank you. I can see Gospel Media. I can see Agbala Jajon. Oh, I can see Oyeniyi. Thank you, thank you, thank you, thank you. I'm happy. I'm happy. Thank you. So, and as I've said earlier, if you have any question, anything that is not clear to you, majority of you know my office. When you are doing fees 107, 107 or 108, there is no way you will not my office. So you will see Ezekiel Omotoso by the door side. My office is always open. Just knock and say, Ezekiel, you explain this thing and I don't understand it. Can you explain it better? Thank you. Okay, let's continue now. So I've actually defined magnetic field, and let's just move a bit further. So is there any, if you can still remember when my senior colleagues taught you electric field, he actually told you that electric field at a point was determined by putting a test charge particle Q at rest at that point. So we can say the electric force is actually the force acting on that particle, which can actually be measured. And we all know that electric field is actually the force, that is electric force per test charge. But in case of magnetic field, I believe you still remember something that I mentioned earlier. That is, magnetic field cannot actually occur. There must be a motion, not static. So that is, for you to determine magnetic field, you must include motion into it. Motion in form of what? In form of velocity. Am I communicating? So that is, we cannot define magnetic field like this because a magnetic monopole is not available. So hence, we have to define in another way, in terms of the magnetic force, exerted on a moving electrically charged particle, not on a static one. Are you following? So that it can only be on a moving electrically charged test particle. Okay. So now, if I go to the next slide now, you will now see the magnetic field where we are going to incorporate the movement. Okay, into it. So in that case, we can now say magnetic field can be said to be a vector quantity. It has already been established, and I've told you that one from the beginning, that it has both magnitude and direction, and that it is directed along the zero force axis. So when the particle velocity v is directed perpendicular to the direction of the zero force axis, we can now say the magnetic field is given as. So it's very simple. What you are going to do is that if you already know the electric field before, I've told you, you don't need to memorize it. Just put, instead of that electric field, replace it with B, which is magnetic field, equal to the magnetic force instead of magnetic field. And remember, when you put test charge, which is only Q for the electric field, but since for the magnetic field is going to associate, it can only possible when there is motion. So just incorporate velocity into it. Am I communicating? So you cannot say, oh, magnetic field is now equal to the magnetic force all over the charge multiplied by all over velocity. So where Q is the charge of the particle. So, and if you can still remember, I said something earlier that a charged particle moving in a magnetic field experience a force. So that is, the magnetic force equation predict the effect of magnetic field on a moving charged particle. So my student, if you are still with me, I want to actually call the second code just to be sure that you are still with me. I want to call the second code now, 6N, 6N, N for north, G for goat, 2, C for cat. That is, I want to type it for you now. Can you see it now? 6NG2C. You got it. Tosco, you got it. Taufik, you got it. Thank you very much. So if you get the attendance right now, we can continue from where we stop. So now that we have defined the magnetic field in terms of magnetic force all over the charge, incorporating the velocity into it. Okay, magnetic force on a charged particle. When a charge is placed in a magnetic field, as I've explained earlier, it experiences a magnetic force if two conditions are met. You know, when you're talking of physics, there are some things you need to understand here. So you need to understand this particular two conditions. You must know it. So that is, if these two conditions are not met, so that means that when a magnetic field is placed in a magnetic field, it will not experience force. So for it to experience force, these two conditions must be met. The first one, it must be moving. You know, I said it cannot occur in a stationary state. So that is, the charge must be moving. No magnetic force act on a stationary charge. That's the first one. And the second one is that the velocity of the moving charge must have a component that is perpendicular to the direction of the field. Mind you, these two conditions must be met for a charged particle, for a charge to produce magnetic force. The first one is that the charge must be moving. The second one, the velocity of the moving charge must be perpendicular to the direction of the field. Is that okay? So since you know that one, let's now move a bit further. So now, as you can see, this particular formula, force on a particle, you can see that the V there is velocity of. You can also see the B, which is the magnetic field. But you remember something in mathematics, when you are preparing for your JAM, they call something called QV call, not multiplication. So you can see that so that this particular one, this V called B, and that's so that the V and B must be perpendicular. So what is the magnetic force if the charged particle is at rest? That is, if there is no motion, there is a way of asking you this simple question. If there is no motion, what happened to magnetic force? I know my student will get it right, yes or no. The answer should be what? Type it for me. I want to see it. When there is no, when the magnetic force, when the particle is at rest, what is going to happen to the force? What is magnetic force if the charged particle is at rest? Thank you. 0, right? Oh, that my friend say, Ezekiel, calm down. Thank you very much. 0, 0. Oh, good. That means that I'm not wasting my time. You are not wasting your time as well. So that is, so what is the magnetic force? If V, there's another way to ask you a question is this. What about if the V is parallel to V, not perpendicular? If it is parallel, what is going to happen? If the velocity of the charged particle is parallel or anti-parallel to B, the answer is still the same thing, is still 0, 0, 0, 0, 0. Okay? It can only not be 0 if it's perpendicular. Am I communicating? So that is, the force on the particle is equal to the charge Q times the cross product of the, as we have actually explained before. So you can recall that in mathematics they say A called B is equal to AB sine theta. So we can now write it in form of this, that is, F is equal to magnitude of Q, V, which is velocity of the charge, multiplied by the magnetic field times sine theta, where the theta is the angle between the direction of the velocity and that of magnetic field. Okay? Yes, since we said magnetic field is vector quantity, it has both magnitude and direction. I believe my student may not want to ask me that this magnetic, how can we determine the direction of this magnetic field? And I believe you still remember what we call the right hand rule, where you actually, let's assume you have a rod, you hold the rod like that, and you actually hold it like the way you can see it on the slide, and your thumb actually up, and you can see your forefinger actually going toward the direction of that magnetic field, and you can see the direction. So that is, if the magnetic field, if the magnetic force is actually pointing to upward, and it's actually the B and V, they are perpendicular to each other, so you are going to actually have positive direction for that of B. But if it is other way around, downward, the negative direction for the magnetic field. So that is, we can say the force acting on a charged particle moving with velocity V through a magnetic force is always perpendicular, not parallel, not anti-parallel. Okay? Thank you. So we can say the FB never has component parallel to V. FB cannot change, but take note of these two different. This is very, very important. You know, before we said magnetic field, velocity of the charge and that magnetic field, they must perpendicular to each other, right? And we said the two reasons that the force, magnetic force, never has component parallel to V, and that magnetic force cannot change the particle speed. It cannot change the particle kinetic energy. It can only change the direction of V. Am I communicating? I said magnetic force can never ask component parallel to the velocity of the charge. It cannot change the particle speed. That is, if it cannot change the particle speed, you know that it cannot change the kinetic energy, but it can only change the direction. But you, with what I just told you now, I believe you know how I can ask you question on this one in objective question, in multiple choice question. Oh, as we recap, okay, I said take note of this. That is, magnetic force never has component parallel to V, and it will not have component anti-parallel to V. It cannot change the particle speed. That is, it cannot change the kinetic energy of the charge. It can only change the direction of the velocity. Thank you. Let's go a bit further. Okay, this one is just what you already know. It's just like when you are actually using your palm just to show the direction of magnetic field. Okay, so if we now go a bit further, yes, I want to remind you something. You know, we said something. If when we want to actually determine the magnetic force, we said E is equal to the charge into velocity of the charge, velocity or magnetic field. And you remember something in physics or in mathematics, that if you want to actually determine the determinant of the V called B, let's assume that we have three different components, where you have component X, you have component Y, and you have component Z. In that case, you can actually do it in such a way as what I actually did on the and you can see it on the slide, where we have I, J, K, Vx, Vy, Vz, Bx, By, Bz. So in that way, you know, we said you can actually write the I outside, and if you, oh, I believe you still remember the determinant. Yes or no? So if you, I believe yes, you say to write down. I believe you still remember. Thank you. So it for solving this problem is that since we said that since they are perpendicular, we can say Q is equal to Q multiplied by V by B by sine 30. So a charged particle moving along or opposite to the direction of a magnetic field will experience no magnetic force. I've already told you before that it cannot be parallel, it cannot be anti-parallel, it cannot be stationary. Okay, so that is why we say it will experience no magnetic field. So also, the fact that there is no magnetic force along some direction, that does not actually tell you that no magnetic field. Magnetic field may actually be present, but no magnetic force in that particular aspect. So that in that case, you can say, we can actually write that F is equal to QVB. If we know that V and B are perpendicular, or if you are calculating a minimum magnetic field to produce a given force. So now let's just use this simple question to actually see if my student actually understand. How many of you can see the question on the slide now? Checkpoint. You can see figure A, you can see figure B, you can see figure C. The figure shows three situations in which a charged particle with velocity travel through a uniform magnetic field. In each situation, what is the direction of the magnetic force on the particle? If you look at the first one, we can see the velocity of the particle is toward the negative side of the x-axis, and the magnetic field is actually going towards what? Towards the y, towards the negative side of y. So if I now ask you, they say, what is the direction of magnetic force? What will be the magnetic of the magnetic force in the A part? I want to see the answer. Oh, it's not clear. Oh yeah, Niyi, you mean the question is not clear? Oh, someone said towards the side of y. Ah, no, the person that said towards the negative of z. No, look at it. You said, when we said the V and B magnetic field and velocity, they are actually acting perpendicular to each other. Since they are on the negative side of X and Y, it's supposed to be the magnetic force will act on the positive side of Z. Oh, Meleki Mayowa, thank you very much. You got it right. Oh, Semilori, positive of Z. Thank you very much. So let's go to the second one. We can see that the V towards the negative of Y and B towards the positive of Z, and you can see it's perpendicular. So if I should ask you what is going to happen to this one, and you can add what is the direction of the magnetic force for this one. Answer. Oh, I believe you want to tell me that it's supposed to be on the negative side of Y. Is that clear? Negative side of Y is the B1. So if you look at the third one, in order not to waste, because our time is actually going very fast. If you look at the C, B on the positive of Y and V on the negative of V, are they perpendicular? They are not perpendicular. That shows what is going to be our magnetic force. No, I need that of C. What is magnetic force? See, it's not perpendicular. I know my student want to say 0. Good. It must be 0. That is, when the magnetic field is not perpendicular to that of the velocity, well, magnetic force is going to be 0. Thank you very much. Let's go a bit further. So let's now display answer to it for you. The answer is now, you have seen the answer already. Good. So you got it right. Okay, before I release you, let's try this simple example. Look at the question on the slide. An electron. If I should ask you, the charge on an electron, is it positive or negative? I know my student want to say negative. Yes or no? Yes, you say it's negative. Okay. So we say an electron that has a velocity V equal to 2.0 times 10 to the power 6 meter per second, I, that is on the component of X, and plus 3 times 10 to the power 6 meter per second, meter per second, the direction of J. And you are actually giving the move through the uniform magnetic field in I direction, in X direction, and Y direction. So if you can see this particular question, if you look at the figure I actually showed you earlier, we have only component X and Y for the velocity. We have component X and Y, that is I is X, J is Y, and we have it for this particular I and J. May I just teach you one simple trick? This simple trick is that, so if you look at the figure we did the other time, that's so that the magnetic, the force, the velocity is on the Y, on both Y, X and Y, and B on both X and Y as well. That's so that the answer we are going to get is going to be on the Z component. So now, if we now go a bit further, we say we want to determine the force on the electron due to the magnetic field. I believe my students still remember the formula I gave you earlier. Oh, good. F is equal to VB, F is equal to QV, but that QV, you're supposed to put cross product in between the V and B. It's going to be Q into V cross product of B. So now, to make the life easy for you, you remember what I told you before from the first slide, where I actually did something on the determinant. But if you don't know the determinant, there is a way of actually doing that. There's another trick of doing that one. So another trick of doing that one is that, but the easiest way is just to use the determinant, okay? But in case you don't want to use that one, I can actually teach you another trick for doing that, okay? Oh, Afam, you got it right, okay? So maybe I should ask my student to actually do this one. Okay, this is the solution. Let me just show you the solution. Okay, the solution is just like this one. We have the magnetic force equal to the Q V cross product of B. and you have it like this one. You have it, you have the Vxi plus Vyj cross product of Bxi plus this J. So if you do it together, you now you get this particular one. So, and since we know that the charge on electron, there is a way of convincing my student to know who actually in the class and understand this better. When you can see that in front of that electric charge, for the electron, I put negative for the electron. So, and in your options, you will see the option that I will not use the negative, just to see if my student actually understand it or not. So if you plug in all those values, you should be able to get that the magnitude is going to be 6.2 times 10 to the power 14. But I now say, okay, but you know, magnetic force is a vector quantity. It must have magnitude and direction. And I've taught you the trick of how to actually get the right direction. Since there is no negative in front of our answer, that's so that the direction is positive Z direction. And now say, okay, my student, what about if I replace that electron by proton? You know that the proton is positively charged, yes or no? So you will now get the negative of the magnetic force. That's so that is going to be negative Z direction. Am I communicating? Okay. So if you now, I believe, so okay, can I give you the third attendance code just to be sure that my students are still with me? That is D776N. D for Dada, 776, and N for Newton. I hope you got the code right. D776N. D for Dada, N for Newton. Thank you. Okay, let's go a bit further before I release you. I want to actually show you another problem. And not a problem. It's just like I want to see if you actually understand it very well. A proton traveling at a 23 degree with respect to the direction of a magnetic field or strength, you are given the angle, which is 3623, and you are actually given the magnetic strength, which is B, to be 2.60 millitesla. But may I tell you something? Some of my students, they said they understand. If you get your question is always too simple, but you may likely neglect that milli. Milli is what? 10 is per what? They said minus 30. Yes, you got it right. Okay, that's so that you must remember to convert that one to the whole Tesla. And you are given the magnetic force. You are to determine the proton speed. So, and you know, if you can determine the proton speed, easily you can actually determine the kinetic energy easily, right? So if I can ask my student to actually do this one for me, you say, V equal to FB all over EQB sine theta, and you plug in all those parameters and you will get the right answer. And once you determine the V, easily you can actually determine the kinetic energy. Yes or no? The kinetic energy is equal to what? Half mv squared. You got it right. So what you got from the speed, plug it in there, and since you plug it in there and you got your answer. And what is the mass of the proton? It will be given. Thank you. So look at this, the next slide now. This is the solution to that one. So before I release you, I hope how many of you got how we got this thing? Okay, but I always tell my students, when you get home, make sure you actually trying to rehearse what I've taught you. I always tell my students something that, if you fail to actually try to actually recap all what I've told you, what I've taught you in class today, it may likely be following me as I'm going out. And I don't want you to follow me. I want you to actually understand it better. So when you have free period, just make sure you reverse something on electric or magnetic field. And let me give you this question, and you solve it for me tomorrow. And tomorrow on Wednesday you give me the answer. Quickly write the question down. Fast. I have less than 3 minutes. Write the question down. A proton is moving with a velocity v equal to v naught j in a region of a uniform magnetic field. The resulting force is F equal to F naught I. What is the magnetic field? That is in form of magnitude and direction. In the above example, what is the minimum magnetic field that can be present? Thank you, just screenshot it and you get it. So since you are screenshotting it so that it can be very fast, let me give you another one also so that you can actually do the thing to do everything together. Am I communicating? I have 2 minutes. I want to give you another question just to screenshot and do it at home. On Wednesday, we discuss the answer. Do quickly screenshot it, and if you get it right, just send it to your colleagues. Okay? Get this question, 2 questions, do it at home on Wednesday. When we meet, we will discuss it together. Screenshot it, send it on your platform, and let them attempt it. On Wednesday, you come and tell me the answer. Nice meeting you again. Oh, the test is going to be June 16. June 16. June 16 is the test. Okay? June 16. So just tentatively is June 16. Prepare very well, and you must make me proud. So this is where we are going to stop physics 1002 for today. Meet you on. No, sorry, a minute. My colleagues want to discuss something with you.
Yeah, good morning, everyone. I hope you all enjoyed the class. Okay. Yes, I believe you've all gotten your tutorial booklet, because starting from probably next week, so I'll be giving a tutorial, okay, that you need to solve and submit. And don't forget that your tutorial will form part of the assessment. So tutorial will take about 10% of the whole assessment. So please, if you haven't gotten yours, it is high time you got it. So take care and have a nice day. Thank you. Uncle.
Thank you very much.
You're welcome.
Mr.